Good evening, friends. We are having now continuation of laminar flow between the two parallel stationary plates. The third part of the derivation, so that is the drop of the pressure head over a given length. So we have velocity equation here, so that we are writing here. So now just rearranging the terms of this velocity equation, so that we want here equation for this drop of the pressure head over a given length. So that is del P by del X. So this part of the equation we need to derive. So del P is the pressure difference and the del X is the difference in the length. So drop of pressure over given length. So we are taking the help of the velocity equation to find out the drop of pressure head over the given length. So just rearranging the terms, we have del P by del X is equal to this. So taking this del X to the other side, then integration of this del P with the integration limits 1 and 2 here. So then here we are having this integration of this uh, part on the right side. So and with respect to here x we are integrating, so this entire thing will be taken as constant. So keeping outside that integration, we have integration of dx with the limits 1 to 2. Integration of dx is nothing but x, so we are substituting integration limits. So we have x1 minus x2. So taking a minus outside, so minus and minus becomes plus. So this x1 minus x2 becomes now x2 minus x1, taking minus outside. So now section 1 is taken at a distance x1 from the extreme end, and section 2 is taken at a distance x2 from the extreme end. Now the distance between the two sections is L, so which is nothing but the difference of this x2 minus x1. So I am substituting x2 minus x1 as L. So we are getting the equation for this drop of the pressure head over a given length. Now we know that HF is the drop of the pressure head, so which is given as P1 minus P2 by rho g, because we know that P is equal to rho g H, so H is equal to P by rho g. So we are having a pressure head in the numerator and rho g in the denominator. So sorry. So taking this P1 minus P2, so we are having a rho g in the denominator. So this equation which is highlighted is giving the equation of pressure head difference over a given length of the two parallel plates. Now the next part is shear stress distribution. We know from Newton's law of viscosity, tau is equal to mu into du by dy. So the value of u, that is velocity, so what we got earlier, so is substituted here. So then simplifying this, we are getting shear stress equation this. So my shear stress is 0 when y is equal to t by 2. So that is exactly at the center of the two plates. My shear stress value is 0. So we are substituting the value of y as t by 2, and we are getting my shear stress equation. So as 0, and my shear stress is maximum when y is equal to 0, that is the upper plate, and y is equal to T, so that is the lower plate. So that is exactly at the walls of the two plates. So substituting our y that is 0 or y is equal to t. So substituting y as 0, so this becomes t minus 0 becomes t only, or substituting your y is equal to t. So we are getting your shear stress value as minus 1 by 2 of this del p by del x into t. So that is the shear stress equation. We have shown all the four parts of the equation, that is shear stress distribution, then velocity distribution, and the ratio of maximum velocity to the average velocity, and drop in the pressure head over a given length of the two plates. Thank you, friends.